Good afternoon, everyone, and thank you for joining us today. I'm Julia Moeller, and I'll be moderating today's webinar. Before we get started, I'd like to cover a few housekeeping items. We welcome your questions today. Please type your questions into the Q&A widget, and we'll answer all of these after both sessions have concluded. If you have any technical difficulties, please reach out as well, and we'll try to help you out. Please also note that the webinar console is fully customizable. You can expand the video to watch in full screen or minimize any modules. And finally, we will be sending out the recording for today's webinar. You should receive that within the next couple of days. Okay, and today we have two speakers. Our first presenter is Ilya Katsov, Head of Data Science at Grid Dynamics. And our second presenter is Charles Jansen, Associate Director of Cognitive Automations at S&P Global. We're going to conclude with some Q&A. So again, please feel free to submit your questions throughout the webinar. And at this time, I am going to turn it over to you, Ilya.
Hello, thanks everyone for joining this webinar focused on COVID-19 response using data science and machine learning. And my first presentation will be about demand and revenue forecasting for lockdown and post-lockdown period. So first of all, let me introduce Grid Dynamics really quick. Grid Dynamics is a data science and engineering consulting services company that works mainly with large manufacturing, retail, finance, technology companies on innovative programs, and we help our clients to perform digital transformation using emerging technologies and data science, machine learning in particular, helping them to optimize their marketing operations using customer intelligence and personalization models, help them to optimize revenues and supply chain operations, and as well as optimize many other areas important for enterprises. And we were recently recognized as a leader in mid-size agile software development service providers by Forrester because of our commitment to emerging technologies and our strategy and strength of our strategy in this area. For this presentation, I'm going to focus on two things. First one is what are our observations about how companies respond on COVID-19 disruption and how their response strategies look like, what kind of organizational changes they are doing to respond to this disruption and these challenges, and what are the use cases that they are focusing on. And in the second part, we will do a deep dive into two case studies. One will be around a company that produces digital media products, and another one will be about a retail chain. And I will talk how these two companies responded to COVID-19 disruption using data science and advanced analytics to stabilize their operations. So if we are talking about of the overall strategy that companies across different industries are taking to respond to COVID-19 challenges, then at a high level, we see that they basically are thinking about three stages or three different aspects of this response. First one is, as you can see, in this illustration, is about supporting resilience and making cost savings decisions in the initial stages of the crisis to provide some immediate response to the challenges that were created by the disruption. Next, many companies actually thinking about how to stabilize their operations and how to recovery after the lockdown and how to prepare for this recovery period properly and how to prepare their forecasting models in particular to support the stabilization and recovery. And finally, the third area is that many companies actually thinking how they can, in the long run, take advantage of the situation, if you will, and how they can gain competitive advantage through implementing some forward-looking capabilities in the early stages, and how they can recover according to a trajectory that goes above the industry average recovery trajectory, as it is illustrated here. And of course, the priorities between the three buckets are different depending on the industry. For example, for industries that were impacted in the most negative way, like retail and manufacturing, the focus is heavily on supporting this resilience and making cost savings decisions. For companies in technology space or in digital media, a lot of focus is actually on how to gain competitive advantage, how to harvest additional revenues created by increase in digital traffic and so on. But at a high level, this is the framework, this is the frame of reference that many companies are using, and this is what we see across the industry. The next aspect of the COVID-19 response is how companies regroup to respond to the disruption and to the challenges. Of course, this response is something of very high priority to all the companies, and typically these response activities, they are led by C-level leadership. What many leaders are doing, they are deploying dedicated stabilization engineering teams and analytics teams that work closely with operation teams across different verticals inside the organization, like customer engagement, revenue management, or supply chain management, helping them to adjust disrupted forecasts, make some corrections, establish new capabilities, and essentially help them to overcome the crisis using different engineering techniques like new features or new performance optimizations for web resources, or doing improvements in analytics capabilities, making model adjustments and so on. And actually figured out that it's very critical to get these teams deployed in time, and companies that manage to do it really quick in early stages of the crisis benefit from that quite a lot. The third aspect of the strategy is, of course, use cases that companies are focusing on. So for our clients, we mainly see two categories of use cases that companies are focusing on. First one is use cases related to immediate adjustments for lockdown impact. Making adjustments to demand forecasting models, making adjustments to assortment to shift priorities towards most important products, making adjustments to supply chain, again, to support distribution and assembly of most important products. These changes, in many cases, were done in very early stages of the disruption. And the second category is about preparation for openings and for recovery during the post-lockdown period. And what many companies are doing, they're trying to do, for example, in-store traffic forecasting and resource planning for post-lockdown period, as well as make adjustments to their assortment and supply chain optimization models in a way that will account for the shocks introduced by COVID-19. So now let me walk you through two quite representative, I would say, case studies that illustrate how exactly some of the companies reacted to the crisis, and what lessons can be learned from these projects. So these two projects were done during last 2 or 3 months. So for the first case study, I will be talking about the project that we did for a media product company, and it was done in early stages of the crisis. As you can see here in the background, we have these famous curves with the number of COVID-19 cases for different countries, and the overlay is the duration of the project. So first one, as you can see, was done mainly in March, and it was about making adjustments to promotion and pricing policies based on the demand shocks induced by COVID-19. And the second project, it is essentially an ongoing project. It was started later on, majority of work was done in April, and the main focus of that project was to forecast how to optimize operations during the post-lockdown period and how to optimize deployment of the workforce across different stores, against based on the traffic forecasts. And for both of these projects, it is important to understand that the main goal was not to apply some sophisticated analytic techniques or machine learning techniques, but the main goal was to implement the solution really quick in a couple of weeks and make corresponding and support corresponding operational adjustments based on the outcome of this project. So proper structuring of these projects and proper project management was, of course, very critical in both cases. So for the first project, the initial problem statement, the initial situation was as follows. We worked with the digital media product company that used to distribute their digital products all across the world to the end consumers. And during our previous engagements, we built for them a demand forecasting model that was used to optimize pricing and promotion decisions internationally for different countries. And this solution is at a high level illustrated on the left-hand side of this slide. So basically, we collect information about sales from digital channels all across the world, from different countries, and this information is extended with some market level data, calendar features, information about these products, like product metadata and so on. And this information is combined into features that are used to forecast the demand for several months ahead in the sales forecasting model. And then the predicted demand and predicted price elasticities are submitted to price managers and promotion managers who do final decisions with regard to promotion schedule, start and date, discount depth for promotions for the next several months based on this forecast. And it helps them a lot to optimize their promotional and pricing decisions. And of course, once we started to experience COVID-19 disruption, majority of these forecasts were invalidated in the sense that the forecasts, they diverged from the reality, or reality diverged from the forecasts. And the goal of the project was to quickly provide some guidance to price managers and promotion managers, at least in some coarse-grained form, and also make adjustments to the forecasts in a way that it again becomes usable for making pricing decisions. So the approach that we took, we decided not to modify the existing production deployment, the existing model, but we decided to do essentially two things. First one was to create this different signal, different series between the predicted demand, predicted revenues, and ongoing observed revenues, and do analysis, particularly for countries that entered the crisis earlier, like China, Japan, and then Europe. And based on that, provide some recommendations to price and promotion managers. What are the similarities between the countries? What are the typical patterns? And how they can use these patterns to optimize prices and promotions. And the second part of the solution was to train a corrective model based on these different signals. So this corrective model predicts the difference between this baseline forecast produced by the legacy model and the actually observed data, and then this predicted error applied on top of the baseline forecast, and corrected, adjusted forecast is produced to more fine-grained tuning of the pricing decisions. So for the first part, we started with very basic analysis. We first analyzed how sales volumes, how demand changed after after the first cases of COVID-19 were discovered in different countries. It essentially happened at approximately the same time during just several weeks, as you can see here on this illustration on the left-hand side, all across the world, across different countries, with relatively small delay between the countries. But what we figured out is that different countries were affected in quite different ways. So the general observation is that demand for the digital media products, it jumped significantly for pretty much all the countries, but the magnitude and dynamics of this change, it was different across the countries. For example, you can see here in this illustration on the right-hand side is that before the first case, our demand forecast was relatively accurate, which is shown here in blue. So for some countries it was slightly below the actuals. For some countries it was slightly above the actuals. But after the first case, there was a significant divergence. Basically, the actual numbers, they jumped significantly comparing to the baseline forecast. And for some countries, for example, for Japan, China, some European countries like France, Italy, the difference was very significant. These countries apparently were most heavily affected in that regard, or they reacted in that way to the crisis with very significant magnitude. And for some countries, the development of this response was relatively slow, and the amplitude of demand changes was relatively low in North America, in the United States, in Canada. It was low in Australia, and in some European countries it was also relatively low comparing to the most affected European countries at a certain period of time. So this was the first observation that we did, is that countries can be different in magnitude, and can be some patterns in that regards that can be leveraged by the price management team. The second observation that we did is that the shape of the shock, it actually differs across the countries. For some countries, we observed a strong immediate shock. For example, as you can see here, for China, there was no major disruption after the first COVID-19 case was revealed in the country, but there was a very sharp jump in sales volume after the lockdown measures, shown here as a dashed red line, were introduced. So there was significant divergence between the baseline forecast and the actual numbers immediately after these measures were introduced. And for European countries, this response, the dynamics of the response was significantly slower. So we see here that after the first case and even after the lockdown measures, the changes were less abrupt, and we see here that there was some sort of a slowly developing response on the crisis. So this insight was used to produce this initial guidance to price managers. We generally made the conclusion that there are some statements that are true for all countries, that the number of users of the product increased across the countries, that the engagement intensity for the digital product increased across the countries, that promo elasticities and advertising elasticity also increased. But at the same time, the magnitude and the shape of the response was different across the countries, and we classified all the countries based on these two dimensions, the magnitude and the shape. And this way we managed to identify some similarities that, for example, for some countries we have slowly developing smooth response, but with very high magnitude. For some countries we have sharp response with high magnitude. For some countries we have a smooth response with relatively low magnitude. And this information was used quite efficiently by price managers to adjust promotion forecasts and avoid the situation then promotions are given in a revenue harming way based on these dynamics observed across different countries. So this was the first step of the project. The second step of the project was to develop more fine-grained models to do more accurate optimization of specific pricing and promotions decisions. And the approach that we took, it was relatively straightforward. As I mentioned, we decided not to touch the existing models, but we decided to develop a corrective model on top of it. So essentially, the approach was that we have some samples of actually observed sales data. We have our baseline demand forecast, and then we are trying to produce adjusted forecast, which is a baseline forecast plus some correction term. And this correction term, we model it as a relatively simple regression model that essentially tried to estimate the baseline forecasting error as a function of the number of days since the first case of COVID-19 was revealed and a number of days since lockdown measures were introduced and some other features, but fundamentally this model was a relatively simple one. And it actually turned out that it is sufficient to make a reasonably good correction to the baseline forecast. So as you can see here, we managed to compensate for this diversion between the forecast and the actual numbers using this simple technique, using this correction model, and make the adjustment that was not perfect but reasonably good for making promotional decisions. And the solution was actually, again, very helpful for promotion managers to make adjustments of their promotional schedule and discount depth based on this corrective model. And of course, the main goal was not to achieve very high accuracy. The main goal was to develop this correction in the shortest possible time, essentially in a matter of days, to provide promotion managers with guidance and with some additional tools that could help them to make better and smarter decisions in this type of a situation. So that's pretty much it about this first project, and let me now talk about the second project, about the second case study that was about doing COVID-19 response project for a retail chain. And this project was substantially more complex technically, and the problem was more complex, but at the same time we had it was started later in the crisis, not in the very beginning of the crisis. So and it was focused on building traffic forecast for the reopening period for retail stores closed as a part of the lockdown. So we had more time to design and implement this solution properly. And the end goal was to produce the traffic forecast that would be used for optimization of store workforce and other resources. And the main challenges still in this project were that the traffic data was available only for a relatively short period of time, for the last 4 or 5 years, based on in-store sensors installed about 5 years ago in this retail chain. And of course, during the last 5 years, there were no major economic disruptions comparable to COVID-19, and it was non-trivial to figure out how this traffic data actually can be linked to major economic disruptions. The second challenge was that stores were mainly shut down on the second week of the outbreak. So we have very limited traffic data that were influenced by coronavirus, and first openings also began only towards the end of the project. So the challenge was that we did not really have good training labels in the sense of traffic data affected by coronavirus to train our models, and we used several workarounds to to prepare properly for receiving this first data after the openings, as I will describe shortly. And finally, the third challenge was that it was not enough just to produce forecasts. These forecasts need to be linked to the actual business problems, which were workforce deployment and allocation. And the way we approached this project was as follows. We started with building a baseline traffic model that essentially was not initially linked to COVID-19 as such. Actually, we had the mainstream traffic model for this retailer already. But we decided not to use it because we needed some flexibility in how this model can be adjusted and combined with other parts of the solution. So we just decided to reuse data and features that were known to work well for traffic and demand forecasting for other legacy models. And we just took in-store traffic data available from in-store sensors and combined it with store properties, store level location, demographics, calendar features, promotional features, and produced a baseline traffic model that was a good traffic forecasting model in normal situation. It essentially replicated the legacy traffic model used to make pricing and promotion decisions by this retailer. But of course, this model was not able to handle the shocks of COVID-19 situation, and to do so, we developed some additional models and combined it with this baseline solution. So the first step towards that was to develop a model that was very focused on establishing the link between the number of COVID cases and some other disease-related metrics and the actually observed traffic. So as I mentioned, we had a relatively limited sample of data that was affected, explicitly affected by COVID-19 for first week or 2 weeks before the lockdown, but it generally was not sufficient to make a good to build a good model and make a good forecast. And what we did, we collected additional data really basically around the number of cases of just regular flu for a long period of time, for last 20 years or so. And this data was essentially concatenated with the data for COVID-19 cases, and we essentially used that as a proxy, as some sort of an approximation of COVID-19 cases. And we built a model that used only these epidemiology features to forecast the traffic. It was not very accurate, of course, but at the same time, we figured out that the number of flu cases, it carries some useful signal that correlates with the traffic, and it has some predictive power. This power is not enough to make a good forecast alone, but it can be used as a component model to contribute into more accurate traffic forecast through combination of different models. The second step was to develop a model that specifically focused on macroeconomic data like the unemployment statistics, income statistics, and so on. And the main goal of this model was to establish the link between traffic and major economic disruptions like the disruption of 2008. Because it was probably the closest thing we can get in terms of economic disruption magnitude to the current situation of COVID-19. And what we did, we collected this macroeconomic data for the last 20 years or so, combined it with calendar data, and tried to build a traffic prediction model using just these two groups of features. One issue here was that we did not have historic traffic data for that long period of time. We had traffic data only for last several years. So in order to train the model on a larger time series that went back to early 2000s, we built an auxiliary proxy model that used to forecast traffic based on sales data. And retailer, of course, had sales data for a very long period of time. And this way, we backfilled traffic data for last 20 years or so using sales data as a proxy. And then we trained our traffic prediction model based on macroeconomic and calendar features. And we, by the way, figured out that the traffic forecast produced by just this combination of features was quite powerful, and the forecast was quite accurate just based on these two features in the long run. And then what we did, we combined these three models together into a unified traffic model. At this point, we also incorporated the consideration that it actually, from the business standpoint, it's better to over-allocate workforce in the stores to provide good quality of service rather than under-allocate workforce for stores and provide bad customer experience. And we incorporated this using asymmetric loss function for model training. And this way, we produced a traffic forecast that used to incorporate regular sales data and all regular features that are used typically for traffic forecasting, but also information about number of COVID cases, flu cases, as well as macroeconomic data. One additional challenge here was that in order to evaluate this model, we generally needed autoregressive samples, because it is, of course, autoregressive model that uses some previous traffic samples to predict future traffic samples, but there was no way how we can if we need to produce long-term traffic forecast, then if we will just use some samples directly produced by these models in autoregression, then it will not be very accurate. Or at least we needed to have some mechanism how adjustments can be made in that regard. And what we did here, we actually used Google Community Mobility Reports to make adjustments to the expected traffic numbers. So the way it worked is that once we had this unified traffic model, it was able to produce some forecasts for COVID-adjusted traffic samples. But then before sending the samples as autoregressive features back into the model to produce longer term forecasts, we multiplied these numbers by some coefficients that are available in Google Community Mobility Reports, which tracks different types of metrics based on mobile devices usage. And in particular, this report contains information about how retail traffic, retail usage, retail engagement numbers are affected by COVID-19. And these coefficients we used essentially as some sort of a proxy to make adjustments to the traffic numbers. Essentially, from these coefficients, we learned how we can decrease or increase the traffic numbers based on the actual information about the dynamics of the disruption. But this, of course, was very crude approximation of what could happen in reality after the stores would be open. And once we started to receive actual information from the first stores that were opened in some states in the United States, we produced more accurate coefficients, and these coefficients were produced essentially by assessing the ratio between the traffic that was actually observed after the reopening, and the traffic from the last year. And then we built again auxiliary model that used to combine these ratios with Google reports, and then these coefficients were used as a multipliers for autoregressive traffic samples. And we dropped the link, the direct link between Google reports and this model as it's shown here. So this slides represents how the final solution looked like. As you can see, there was quite a lot of extensions comparing to baseline traffic forecasting models. We built a dedicated version of this model specifically for this project. We built a dedicated model specifically to account the number of COVID cases and different disease-related information, and we built a dedicated model for macroeconomic factors to model massive economic disruptions, like disruption of 2008, and incorporated into the model as well. And we also built this workaround related to autoregressive traffic samples to prepare better for getting new data after store reopenings. And this actually helped quite a lot to produce reasonably good forecast. Again, it was not, as we currently see, this forecast is not very accurate comparing, for example, to regular demand forecast. And this is expected because we deal with situation that is fundamentally unpredictable and unforecastable. But at the same time, it helps a lot to make adjustments to the workforce deployment and optimize other supply chain and logistic decisions in a way that account for disruption in the best possible way. And this is, of course, very helpful. And in general, it was a very wise decision to build this type of models ahead of time and prepare for reopenings this way, so that operations after reopenings can be optimized immediately once reopening starts, and new data can be incorporated into the model immediately as this new reopening, new sales data is available. So let me now summarize the lessons that we learned from these two projects, from these two case studies. So one of the interesting lessons was that it's generally possible to rapidly respond to major disruption like COVID-19 using advanced analytics and machine learning, and some meaningful projects can be done in just 2, 3, or 4 weeks and deliver some reasonable value. It's probably against the current belief, the common belief that machine learning projects, they typically take a lot of time and need some prototyping, and typical timeline is measured in months. Actually, this is not necessarily true. It's possible to do meaningful projects in just a matter of a couple of weeks. But of course, the project needs to be defined in a reasonable way and managed properly to make it happen. The second lesson learned is that direct executive support and early deployment of experienced data science teams is very important and critical, because these two projects, as well as other similar projects that we did, they would not be possible without experienced data science teams that could implement this solution efficiently and rapidly. And of course, it required a lot of support from the client organizations at all levels, because all obstacles, organizational obstacles, and so on needs to be cleared to make this type of response possible. The third lesson is that it's probably most important one from the technical standpoint, from data science standpoint, is that it might not be possible to predict unpredictable things, and obviously major disruptions like COVID-19 and many specific things like store reopening schedules and so on, they are not really predictable. But what can be done in this situation? It's possible to develop models that structurally can accommodate for this type of changes and make some assumptions on what can be good predictors and how new data can be incorporated. For example, in the previous case study, it was information about the number of flu cases or information about macroeconomic shocks. And if you develop a model this way that makes these plausible assumptions, then you can quickly incorporate ongoing data once this data become available. And it actually relates to the next lesson learned, is that in projects like that and in situations like that, it is very important to incorporate and look for and incorporate unusual data sources like international data, experience of, for example, other countries that entered crisis in earlier periods of time, or incorporate unusual data like epidemiology data to make adjustments, and this is quite a natural conclusion, because if we deal with unusual situation, then we need to look for unusual solutions and unusual data sources and unusual way of redesigning our models. And finally, last but not least, it's very important to manage such projects properly, just like any other emergency projects, because it's not always possible to achieve high accuracy or some other good technical metrics, but it's definitely possible to do these projects in a reasonable way and to produce some useful insights and do some partial solutions that are able to produce useful information for that can be incorporated into business operations. For example, it's not necessarily needed to produce very accurate forecasts, but it might be very helpful to produce some insight into the shape and magnitude of disruption by different countries or by different regions, and this information can be sufficient, for example, for supply chain managers or for price managers to make adjustments in promotional calendars or make adjustments in assortment decisions, at least in the early stages of the crisis. And then the solution can be refined and more accurate models can be developed, as we've seen in the first case study, to do additional tuning of these decisions. But of course, the first priority is to produce these at least crude insights in the early stages of the crisis, and produce insights that are possible to produce rather than focus on perfection and accuracy. And I believe that these are very, very good lessons and very good techniques, and these techniques are generally applicable not only to the current situation, to COVID-19 crisis, but they generally, these rules, these best practices are applicable to majority of major disruptions, including economic ones and disruptions of different nature. Yep, so this is pretty much it. Thank you for attention, and thank you for again for joining this webinar, and I'm ready to take questions. Thank you.
Thanks so much, Ilya. Just a reminder, we'll respond to any questions after both sessions have concluded. And at this time, I'm going to turn it over to Charles Jansen, who is going to speak about COVID data analytics.
So the idea, the goal of today is to create this. So you might, I'll put this video. You might have seen that kind of video in YouTube or in LinkedIn or in some social network. So the first thing you need to know to create that kind of video of visualization is actually to know how it's called. It was not obvious to me when I started. So it's called a bar chart race. So once you know that, you already know a lot to be able to actually do it, and you could Google it and find a lot on your own. But on this video, what we'll do on this call, what we'll do is show you how you could create exactly that kind of video. So here we're working on the data from the COVID. I got the data from the cases, I got the data from the deaths. So we'll look together how to get this data and well, do your own. So here we see that it finished, this video finished in April because I did it at that time. So we'll do a new one, which will be better than this one because we'll have more data. So how would you start? So first we'll be using this tool. So that's where you actually see the visualization done. There's a lot of things that can be changed here, and we'll review that. We can decide the shape of everything. So what does it want to be able to work? So what this app is looking for is the data per day in columns. And here, if we want to work with countries, then we need the country in the first column. Then if we want to add something else, like the flags, because it looks good to have the flags on at the top of the line, then you actually need to provide those flags as a link that this web page can look and get the flags. So that's everything we'll do. So we'll be working with Spider. So here I put some link that I use, some links that we could use, and the main links that I normally watch. So let's look at those links one by one. This first link is pretty famous. That's Worldometer coronavirus. I think most of the visualization that some like the university are using data from this page. What I couldn't find is how to actually download everything. So I checked that in April again, maybe it changed. So here we got everything, and we got also the data about how many people actually recovered from the virus, which I thought was an interesting data to work on, but I couldn't find a good source of data with just that. So we'll be working on cases and all this, which is, well, basically the same to work on. With the thing is, well, the amount recovered really depend on, well, the amount you tested, right? So if you don't test too much, then you don't have many cases, then you don't have many people that recover. So the deaths from this aspect are a bit more trustable as a data, even if, again, it depends how the country are collecting the data, etc. So the data I used here came mainly from this, so that's the European Center for Disease Prevention and Control. And they are updating the data every day. So here we're recording this with 8. I downloaded it yesterday to recreate all this code again. So I'll keep working with the data that I have from yesterday, but you could just download there, and there's different format. You can have it in CSV, in JSON, XML. It's kind of strange how you download it. It's actually just call it download and do not have .csv or anything like that. So you have to rename it. So what I did is I renamed it, and I got here the data as data. I call it data, and we'll look at it like very soon. But also what I wanted to do in this presentation was to add some more data so that you could actually look at how to create a different race bar chart. So here, oops. This is another one. I'll take this one. So here you can, that's our World in Data webpage. So I'm not sure how trustable it is, but it looks pretty good when you look at it. The numbers are different, so that's something pretty important, and we'll look at it with actual data. From one set of data to the others, they don't have exactly the same number. So it really depends on how they decided to count the cases, etc., based on what was available in different countries. But here the same. You can download Excel, JSON, etc. So I downloaded the JSON and I left it with the same name, if my memory is good. So I can close this one again. And here we had one more, which is a WHO organization. And so all the links will be in the code. But so here they got a lot of different, possible data frame we could use, CSV, etc. This one I'm not using today, but if you're really interested in data about COVID, that's another one that you could look at to complement your data. Good, so now we need to get the data in this shape. That's what we'll do starting now. let's go back to Spider and actually start working on the data. So Spider, I know, is not the most used maybe IDE. People like Jupyter Notebook a lot. When working with big data frame, I think Spider is great, and I'll show you why. Basically, you can just watch them super fast without having to go scroll up and down or rerun stuff. So we'll import pandas. We'll open those to CSV. I've got the code on the side, so I'll just copy paste for the sake of time. So I imported pandas. I opened those two data frame. So the first one, this is the one from the first link that we looked at, the European Agency one. Here what we see that we have the data per country, and we got the data per day in a descending way. Then, well, we got different way of looking at the data again, and we have some code of the country, and then we got the population of the country, then we got actually the COVID data, which is the cases and the deaths in a day-to-day basis. So most of the source of data are reporting the data this way, as far as I could see. So it's just about formatting it a bit so to have it in the shape that the app is looking for. Something pretty important, the app, when we look at the video we had here, let's go quickly here. We can see the date here. So it actually works in alphabetical way. So you need to have a 0 here. You need to have a 0 here. If not, everything will be out of order. So that's the initial data. And here we can see that the order of the data is not good. So we need to work on that. Let's look at the other data frame. The other data frame got way more columns, more or less the same amount of line, which already shows the data is different because it was from the same day. What do we see? Again, countries. This time we got information about continent. We got the date in a shape that would be more usable. But when I did the code, I used mostly the first data frame. So I'll be using everything from the other one. Here then we got total case, deaths, etc. But what is really interesting from this one is that we have, well, again, the population. We got also the population density, which we didn't have. So it's always the same per country. So that's exactly what I want to enrich my first data set with. We got the median age of the population. We got some indices around the age 55 older, age 70 older. We got the GDP per capita. We got some information about poverty. We got the COVID death rate, diabetes prevalence, etc. So there's a lot of information that we didn't have in the other Excel, in the other data frame. So I'm not really interested about using the data per day from this second data frame. So I'll just create a new data frame from it where I'm using only the last data per country. Why only the last data? Because this one is actually descending. So I don't want to take the first line. I want to take the last line, let's say for Afghanistan and for all country, because that's where, well, I'll potentially have more information since they have a line like this with total. So this one for this country is not filled, but in some other countries they do. Let's see if I can find one like here. So we see the data is growing. So I'm definitely more interested in the last one compared to another one. Well, here we see it might be an exception. Cool. So once we got that, I just create this new data frame and now I can look at it. And I have here, so well, explain the code a bit just in case. We're doing a group by ISO code because ISO code is something that we had on both data frames. So if we look at the first one, I kind of need something to allow me to merge them, right? So here I see that the country territory code is like this. And if I look at the other one, now you understand maybe why I like Spider that much for that kind of thing. I can look at the data frame like that. So here we see, okay, the ISO code is kind of the same code, right? So I can merge data using this. And here now, I did a group by on this and I took the last one each time. What do we have now? We have the index in an alphabetical order. And that's basically all the country, and it's the last line of every country of the second data set. So now I have all the data per country, keeping only one line. And well, these things that I'm interested, that was repeated all the time, like for instance, the stringency index, population again, even if we have it in the other one, density, etc. So that's what we'll be using. Now, let's use this to actually have only one data frame. I'll add more lines so I can go down easily up. So what are we doing here? We'll merge those two data frames. This one, the first one we're actually interested in, and the one that we transform from the second one, which is giving us this extra information about stringency, density, amount of people of a certain age, etc. So the merger in Pandas is very similar. It can have the fields of SQL. So you got an inner join and you define who's on the left, who's on the right. Here I'm just saying I don't want to use index and I want to be, the columns we want to merge things will be, as we saw, country territory code for the left one, which was the first one, and the right one, the ISO code. And I created as a new data frame so we can see the difference. Here we see, well, we got more columns, which makes sense because we merge those two, and the amount of line will be the one that could be joined. Good, so that's the data set, the data frame we'll actually work on. And we see, okay, that's the date in the order that we had initially. This is all the data for the first one, the case, the death, the country, and then, well, this we had initially, and then we start getting information about the next one. So now I got, for every day, I got all the information that I could want with all the data from the country. So we'll look at it again soon. Now, next step. So the next step will be, because of the way this is, and so you can decide the size of this left panel when you got the name, but you don't want it to be too big, because if it's too big, then it's going to be all text here, maybe up until here, and well, that's not what you want to show. You want to see mainly the bar. So some names that I identify as being a bit too long, I'll just replace and give a shorter version. So here we see Antigua and Barbuda. I'll just call it Antigua, United Kingdom, UK, United States of America, USA, just a few like that we know we're probably going to see. I run that. So I just edited directly the data frame. And I'll create a new column for the date. As we mentioned, the date has to be in a shape that will be an alphabetical order. So I need to keep the 0, and I need to keep, well, the 0 in the month and in the day. So I'm just running this. That's not the cleanest way of doing it, but it works well here. I can show you what it does. So if we go back in the data frame, and here we see the date was in this order. Now I look here, it should be the last one. It's not there because there's more column. Oh no, it's because the second data frame actually add a column named date, so it replaced it. It's here. So here, now we got the date here. It's in the shape that I want. We got 0 before months that are below 10. So we're good here. Now, if we look at the data and we just look at the amount of cases from one country, it actually doesn't mean much, right? So what we really are more interested in is the amount of cases based on the population of a country. So what we'll do is define what would be the size that we want to work on. Here I'm picking up 1 million, exactly like they're doing on the coronavirus page. If I go back to show you here on this table, it's loading. We see that, well, most people will want to look at what is the amount per the amount of 1 million, you have of population in this country. Because if you got 3 cases in a country, or let's say 3 million cases in a country of 3 million people, then it's everybody. If it's in China, then it's a small percentage, right? So that's why we're looking at it this way. So we define the size of the group we want to look at. What I'm taking is the data I have from the population. We can look at it again. So pop data here, that's the amount of people days in the countries, population of each country. I'll use this. So I divide it by 1 million, so it's not too big number. And I'll just create a new column, which is, okay, the amount of 1 million population this country has. So I'll run everything and then we can look at what we've been doing. So we got this DF1. So DF is the original one we had. This time it's going to be at the end because there are new columns. And we got the amount of 1 million people, 1 million we have in the population. So here we got 37, that's because there's 37 million people. And now we got the amount of case divided by this number. And then it's way more interesting to actually look and understand, okay, what is actually the scale in this country? And the same for the death. Good, so now we're good here. The next step will be, since we're working on this data frame, I just collected and I had handy, so I will just copy paste them, all the flags that we need with all the links. So basically that's all of the countries that we tend to have in this presentation, and I'm taking all the Wikimedia flags. So I'll just run that, nothing really interesting here. I'm just, creating a new flag column and then filling it with some of the country. I'm just not adding everything. There's probably a better way to do it. And there might be some library that give you the flag automatically, but here just do quick and dirty. I go back to the data frame and now I got the flag. I don't have the flag for everybody. I got the flag for some, right? And it's repeated again, like the rest of the data. So now we don't want to keep working with only repeated data. So what we'll do is this. I'll create a new unique data frame with just one line for each country, but now using the data from this last data frame that we have, right? So I'll run that. And let's look at it. So now it's unique data, so it's here. And that's the one we can do a lot of things with. So basically, what do we see here? We got all the data per country. So here it's really easy to read. We're looking at country and not the code. I'll show you how this was created just in case also. And we got all the data we wanted from the previous data frame and more. The problem is that there is way too much data, right? There's a lot of stuff we're actually not interested in. So I'll trim a bit first. How to trim fast? Well, actually just look at all the columns that we have. So I just run this. And here I got a list of all the columns of this data frame. So basically what I did is I just copied that, and while looking at the columns of the data frame here, oops, not this one, the unique one, I basically start to define, okay, do I want it, do I don't want it? So this one, days, etc. All this for the unique one, not interested, not interested, not interested, up until keeping some of interest. So the list that I had was, I'll show you again, the list. So here it's after I edited. So basically I left any name from this list that I don't want to keep, anything that I thought, hey, this one, maybe keep it, then I'll delete that. Then I kept. Here, what I did before, just to define how this data frame was created, well, I just created it on top of the country and territories. This time first, because we saw that it was descending. So I'll run this. And now we got a much cleaner data frame, sorry. And we can start to think of what else could we do? We're going to look right now only at the deaths per million of population, but there's a lot of other things that could be looked at. And that's where we could start some analysis, because for instance, we got the stringency index, right? How hard is the country on people basically here to kind of see, is it the kind of thing that affected the amount of cases that they had. So here, I think I removed the amount of deaths. We could actually leave it just, I'll rerun that, and I'll keep the total deaths, let's say. We can even keep the total cases. Basically, I'm just saying, okay, just saying don't delete that. I just recreate the data frame, rerun that. Now we got those two columns again. I can look at them again. So total deaths, total case, total deaths, and let's say, okay, let's order by, it's the last line. So it will be better to actually look and order the data here, this one. So basically the idea will just be to order like this and kind of see if, okay, when the stringency is super high, how is the result, right? So if we see that this number is really good or really bad, I'm not sure this one is actually the one we want. We need to look that it's actually the last line each time. But that's how we would look at that to see if there is some interest in this data. When I look at it, I couldn't find anything really of interest. And the main issue is that most of the country don't have data that feel really trustworthy. Then there is a test unit. So looking how many tests were done, it's interested, but then we see that there is different way that it was reported. The people tested, the sample tested, the test performed, the unit might be unclear or we don't even know. So again, it's like, I don't trust this data too much. Then there was the population density. I said, wow, the population density might be super interesting. But the problem is that in some country, let's see, I got it disordered, I'll open it again. If I look at Argentina, for instance, where I'm based right now, we see that the density is super low. So this makes this data totally useless to me. Why? Because yes, the density of the population in Argentina is really high, is really low because the country is big and there's not that many people in it. The problem is here, most of the cases are situated in Buenos Aires. So actually the density in Buenos Aires is really high. So this data will just, not help at all because whatever I would use it for would kind of tell me, hey, all the other data points from Argentina are for a low density case and actually a high density case because it's everything in Buenos Aires. So I was not really interested in this. There's probably a lot of things that can be done around the median age, because I think this data point is definitely trustable. Around the GDP per capita and kind of check if, if we can want to create some visualization around this, but it would be more a graph and histogram, something like that, not really a raised bar chart. So we'll just continue with what we have here. This was mainly to see and show, hey, actually we could do way more with this data. So maybe you want to explore it a little bit more. I'll just delete all those data frames that we won't use anymore. So I don't have them here anymore. Up. And here I'll filter the data because the problem here is that we got really a lot of country and without, offending anybody, there's some of them that we might not be really interested in looking at for visualization, depending what our goal is, right? But if we go back one more time, I should not close it, to this web page. And we order the data, so it will take some seconds to load again. We order the data by what I'm interested in here, which is basically the deaths per million of population. Well, most of the very high one, or many of the very high one are like this: San Martino, Andorra. So there used to be more a small country like that: San Martin, Isle of Man, etc. So again, it depends on what you want to show, but in this visualization, I'm more interested in showing Europe country, big countries that people might recognize easier. Again, it's really up to you if you want to do that or not. So what I've created is a filter, and I'm saying, okay, I'll use only the country with more than 10 million people, right? So this filter already a lot. So I'm using the filter here, and we can start reviewing a bit more. Oop, I didn't run that. So this one will fail because I already deleted. I just need this. So unique data review. Here we are. So unique data review. Here we got way less country. Why? Because we got only country with more population. So basically it started at 10 million and it go up to China. And well, it just help in, if we want to continue the kind of analysis I mentioned before, it can help because, I don't know, let's say, hey, is the median age related somehow, like quick view, right? Obviously we should do more, but to the stringency index. Yeah, maybe it would worth be digging a bit more. If I go the other ones, I see, well, the younger they are, it seems that the more stringency we had, etc. So that's obviously for more analysis, etc. But it helps to have, when you want to have a quick view, to have less data. And I'll keep this reduced amount of data for the bar chart race. So now I'll pass just everything that remain at once, and we'll look at it together. So we were here. What we want to do now is create this shape of data that we want for the Flourish app. And it was the column in one, like the day per columns and the country per line, which is still not what we have, right? We're still exactly like we were before. We just filter a bit and we just add some column and merge the data. So how to do that? Well, it's actually pretty easy, and it looks a lot, for those that are familiar with Excel, it's like the pivot table in Excel, really similar. So basically, you have to define on what you want to create your pivot. Here in that case, that would be the case per 1 million, because that's what we want to graph, right? And what I will use as index, so that's the country names. Then we define the column, which will be the date, and how we want to aggregate the data. Because here we actually want to aggregate the data. Because if we look at what this app is looking for, I'll show the data again. It's actually, I'll go a bit like this and like that. It's actually looking for, it's not smart, right? It will just show the bar with the numbers A's, right? So it won't do the aggregation, it won't aggregate data automatically. You have to provide the data already aggregated. So if you just give the amount you have per data, well, per day, the amount of days, let's say you have per day, then the bar will be changing all the time, etc. You actually need to aggregate and keep, you know, the amount from all the previous day plus the amount of today and have it here. So that's what we'll do here in the code by defining the aggregate function. And then we're good. So basically, here I'm doing the sum for the aggregation. And for the flag, I take the data from the unique flag. For the 1 million pop, the same. I'm using this data frame we had, so this one. Because I lost data while doing the pivot, so that's why I'm using this. So initially, I put everything on DF, on the data frame, and then I'm keeping the data here, then I'm losing some data when I'm doing the pivot, and then I'm actually putting back the data there. So if we run it, you'll actually see it. Let's run only those lines, so then we can remove the last one. So that's the case per 1 million. So now we got the shape we wanted. The country, exactly like the web page one. We got the days, order in an alphabetical way, which is the way that we define. And then I can just go on. Here we see, well, it may be easier with something that start. Here we see that it's all the same number. Okay, Australia. So we see the number is growing, right? So that's a sum. We've been accumulating all the data, and we're good. We got exactly the shape we wanted. What I'll do now is filter out all the country with, you know, less than the minimum population that we define above, which would be here. So we had, if we look at the data frame size was 203 by 162. I run this, now we got only 88. I can open it again. And basically we got those 88 countries and we're ready to go. So we'll do exactly the same for the deaths. Here, it's exactly the same, right? We do exactly the same steps, so I won't go over it too long. The data frame is very similar. If I go, you know, far on the left, far on the right, well, everybody start to have data. I kept that's what I did at the end, right? I kept the amount of, I kept the flags because I need to provide the flags to the web page. And this one, I think actually I don't need it. Good, so now what's the next step? Well, we just need to export that. So pretty easy. I think I already have it, but I'll run it again. I'm not keeping the index, and I'm just, no, actually I'm keeping the index because it's commanded, because the index was the name of the country, right? Cool, so let's look at the Excel we created. I got it here. Let's look at this one per 1 million pops. That's what we just created, right? I look at it in Excel. So that's exactly the shape of the data the app is looking for. The date, the country, the accumulated data, then the flag. So let's use this. And we're almost done. But now we'll look a bit more at this app. So, well, you need to log in. If you have a public account, then all the data that you put in this web page will be public. So be careful on what you're uploading there. The uploading is pretty easy. You just upload data, you select one. So let's say we said deaths per 1 million population. Import publicly, they remind you, hey, careful, it's going to be public. So it really depends on what you upload, right? If it's public data like here, you're fine. If it's data about something else, well, if it's anonymized, you're fine. If not, well, use your best judgment. The row were important. Next, select the column. So that's actually super intuitive and super easy. Here you got the name of the columns. The label were an A. So I just confirm, yes, the label were an A. That's the shape of the Excel I created, right? Then we go from B to FE. That's all the data. Then we define the image we want to have, that's the flags that we've been collected, and we add it to the data frame, and that's it. Yeah, this last column, we didn't need it. And we're good to go. So basically, it's already doing a small demo. So let's look at it. Nothing is happening much at the beginning. So let's start at 28. And there's something fun I want you to see. So let's look at it 100%. So we saw as Italy exploded suddenly, but here it's not just the amount of death, right? It's relative to the size of the population of the country, the population size. So we see that then Belgium really came. The US are growing slowly, but they're actually pretty low. France is pretty high. Sweden is going up. We're in May. We continue to go, oh, what happened? If we go back, you'll see that there's something crazy that happened that technically is impossible. Is we got this, look at Spain. So Spain is almost at 600, it goes over 600 and suddenly it goes down. So this is impossible. I mean, that suddenly you got less dead than before based on the amount of your population. So, well, here at least is, aside from the fun aspect of it, we saw that it showed us something about the actual data. There's something really wrong. So let's look at what happened. I go back to my first frame. I open it again. So it was the F1. And I look at the case and okay, what happened? Okay, so some countries are just giving negative amount of deaths sometimes. So, well, I actually saw that looking at the visualization. I could have checked the data obviously more at the beginning. It's not something that was obvious to me that they would do something like that. So they probably decided that some count were not right, and it was pretty recently and in a really big amount for Spain. And well, that's exactly what we've seen in this visualization, how suddenly, you know, we're here and it's going down. And then if we go up to the end, well, UK is going up, then well, it's automatically start again. I can just pause it. And that's more or less where we were 2 days ago. I can go one day more. So yeah, so the good thing about the app is that it's highly customizable. Let's say if we want to have only, let's start here, I'll play. I want to have 15 bar. Then I just have to do that. Everything is done automatically. So it's pretty easy to work with. If I want to have just 5 bar, then I just put 5 here. If I want 20 bar, then I can see all the 20 bar moving, etc. Obviously, well, I would need to add maybe some flag at the countries that are not there, like Dominican Republic, format the name as I did for the other one. And we're done. So basically, there's more things you can do. Like for instance, if we look at the number formatting, well, you can define the amount of decimal you want. So at the beginning, it doesn't look everything with a 0, 0, 0, 0. Let's put just in bars. And I could actually have way more if I want to have more data from the beginning and have like that here. So at the beginning, they were reporting less often, etc. Now this really starts. Cool. So that's all for this presentation now. We'll take some question. Happy to answer you. Thank you, everybody.